Greetings. Welcome to the 13th lesson in a series of lessons on basics of power systems engineering. This lesson deals with impedance of AC circuits. In lesson 12, I discussed the phasor representation of voltages and currents. These phasors form the variables that determine the state of the AC circuit under consideration. The structure of the AC circuit, however, is determined by the elements that form the circuit and by the way these elements are interconnected. Among the most fundamental of the AC circuit elements are resistors, capacitors, and inductors, seen here. These elements are collectively referred to as impedances in study of AC circuits. This lesson covers these three impedances and various ways they may be interconnected to form AC circuits. Here are each of these elements separately drawn. The unit for the quantity of resistance shown here is ohms, which is indicated by a capital letter, Greek letter omega. For inductors, the unit is henries, and that's abbreviated to H. And for capacitors is farads, abbreviated to capital F. Let's assume that an AC current of I is passing through each of these elements. This current will cause a voltage drop across each element. The magnitudes of these voltages are shown on the next slide. For resistor, the voltage would be I times R. For the inductor, the voltage drop magnitude would be I times omega L. And for capacitor, it would be I times 1 over omega C. Omega is the angular frequency, and it equals 2 times pi times the ordinary frequency, which is 60 Hertz in the United States. Here you see the Ohm's law written for AC circuits. It is essentially the same as the one written for resistive circuits, except that the R in V equals IR has been generalized to Z to represent the AC impedance. So they're the same equation basically, except that R has been replaced with Z. Impedances in AC circuits are commonly assigned letter Z. Comparing this equation to each of the three equations on this page, it's clear that Z is equal to R in the resistive circuit. Shown here. And again, comparing this equation with this one here, it is seen that Z equals omega L for the inductors, written out here. And for the capacitive circuit, Z is going to be equal 1 over omega C. For a resistor, the voltage across and the current through it are in phase. For example, if a current of magnitude I with a phase angle of 20 degrees passes through the resistor, having I here equal a magnitude, a quantity with a phase angle of 20 degrees, the voltage will have the magnitude of IR and the same phase angle as 20 degrees. However, the voltage drop across an inductor will have a phase angle that's 90 degrees greater than the phase angle of the current through it. Once again, if I assume that the voltage here is, or the current here is I with 20 degrees, the voltage drop across the inductor would be I times omega L, as shown here, but with 20 degrees plus 90, which is 110 degrees. And the voltage drop across a capacitor will have a phase angle that's 90 degrees lower than the phase angle of the current that goes through it. So if I use the same current here for my example, I have I with 20 degrees of phase angle, then the voltage across the capacitor will have the magnitude of I times 1 over omega c, but this angle would be 20 degrees minus 90, which results in a negative 70-degree phase angle. To represent the phase shift for the inductor in voltage, we precede the omega L with a J, so the full form of the impedance for the inductor would be Z equals J omega L, because we know that multiplication by J will advance the phase angle by 90 degrees. J, of course, is the square root of -1. And for the case of the capacitor, the full form of the impedance for it would be Z equals to negative J times 1 over omega c, because negative J causes the phase angle to be retarded by 90 degrees or go back by 90 degrees. Those are written on this slide. So the full form of the impedance for the inductor is this, and for the capacitor is this, and for the resistor remains the same as it was before. So with this, it is seen that the impedance of an inductor and of a capacitor are purely imaginary. There is no real part to these, while the impedance of a resistor is purely real. There is no imaginary part in that one. Interconnection of these three elements form the whole or part of practical AC circuits. Knowing the impedance of each element and the rules for series and parallel combination of impedances, we can find equivalent impedance of most circuits. The exceptions are circuits with delta or Y connected impedances, which will be covered in the next lesson, lesson 14. Evaluation of equivalent impedance is done in ways that are parallel to evaluation of equivalent resistance in purely resistive circuits, except that here the operations are mainly operations with complex numbers. Assuming that the viewer is familiar with resistive circuits, I will move directly to doing some numerical examples that require calculation of equivalent impedances. In this first example, we are given the value of a resistance in ohms and of an inductor in millihenries, and for a capacitor in microfarads. We are asked to find the impedance of each, assuming that they are to be part of an AC system with a frequency of 60 Hz. The answer for the first element from left is immediate and is as well independent of the frequency. It is just 5 ohms. You can see that here, Z equals 5 ohms. For the inductor, I will substitute 2 pi times 60 for omega, and will substitute 40 times 10 to the power of -3 for L, and find the product and precede the result by the letter J. You see that here, J times 2 pi times 60, that's for omega, and 40 times 10 to the power of -3. 10 to the power of -3 is to account for millihenries. And the result is going to be 15.08 ohms with a J in front, of course. J, 15.08 ohms is the impedance of this inductor. For the capacitor, I'll have negative J times 1 over quantity 2 pi times 60 times 200 times 10 to the power of negative 6. And that's written out here. This is the omega part. 200 and 10 to the power of negative 6 accounts for the microfarad part. And the answer comes to negative J times 13.26 ohms, shown here. In the rest of the examples in this lesson, I'll be using these three impedances that have been pre-calculated here. Before continuing with the rest of the examples, I would like to take a short detour to introduce myself. My name is Fuad Alvandi. I'm a PE in Electrical Power Engineering. This is the 13th lesson in a series of lessons on basics of electrical power engineering that I have published on the YouTube. You find my name, web address, and email address on this slide. You can visit my website, where you will find comprehensive modules on topics in power systems engineering. The website is own-your-destiny.mylearnworlds.com. If you're looking for a resource to review topics in preparation to take the PE exam in electrical power engineering, you will find the modules on my website to be helpful. I will now continue the lesson with example 2. This example asks for equivalent impedance of the series combination of a resistor and the inductor from example 1. The impedance of the inductor was found in that example and will be used here. Since these two elements are in series, the equivalent impedance will be the sum of their ohmic values. Z equals 5 plus J 15.08, and the unit for Z, of course, is ohms. The equivalent impedance is a complex number in this case, which can also be represented in its polar form as a magnitude and an angle. In polar form, it's 15.89 ohms with 71.66 degrees. This exercise has the resistor and the capacitor of example 1 in series, again using ohmic value of the capacitor, which was found in example 1. The equivalent impedance would be sum of the two, again, would end up a complex number. First, I'll show it in its rectangular or Cartesian form, 5 minus J 13.26. And now in polar format, 14.17 ohms with negative 69.34 degrees. Example 4 has all three elements in series. First, converting each element to their ohmic value, again borrowed from example 1, we have those. 5, J 15.08 for the inductor and negative J 13.26 for the capacitor. We'll add these to get the overall Z. 5 plus this one plus this one, and simplifies to Z equals 5 plus J 1.82 ohms. In polar form, it comes to 5.32 ohms with 20 degrees as its phase angle. For the last example of this lesson, we have the series combination of the resistor and inductor placed in parallel with the capacitor. Again, their ohmic values are shown in this diagram. The series combination of the resistor and the inductor, of course, is 5 plus J 15.08. For the parallel impedance, just like the case of parallel resistors, we take the reciprocals and add them and then find the reciprocal of the result. Let me just draw as a review. If we have two impedances, Z1 and Z2, and we're looking to find their equivalent impedance seen from here. Well, 1 over Z equals 1 over Z1 plus 1 over Z2, just like the case of the two resistors in parallel. Using the numerical values for these, for this branch, I have 5 plus J 15.08, so 1 over that, plus 1 over the ohmic value of the impedance for the capacitor, add up to 1 over Z. I have just calculated the inverse of this one, which is this complex number, and the inverse of this one, which is this purely imaginary number. And simplifying these two together, because they're both purely imaginary and add up, we get 1 over Z equals 0.01981 plus J 0.01567. Now to find Z, we will have to invert the right-hand side, so 1 over this quantity, and that's shown here. And once again, if you put this number in your calculator and do an inverse for it, you'll get the answer for Z, which is 31.05 minus J 24.56 is the equivalent looking into this circuit, equivalent impedance. And in polar format is 39.59 ohms with negative 38.35 degrees. We have reached the end of lesson 13. This is Fuad Albandi. I'm the founder and instructor of the online educational site Own Your Destiny. If you enjoy watching my channel, please click on the subscribe button and the notification bell. Thanks for watching this video, and I hope to see you in another one of my presentations soon.